right. All right. So now we're going to have our main speaker. So her name is Jade Abbott. She's going to be doing a talk on machine learning in real life. She is a actually, let me get up here. She is a data science. Sorry, not data science. Machine learning engineer. Wrong term. I know we discussed this. It's just I don't know why they get mixed in my head. And she's also a full stack developer, and she works at RetroRabbit. Alrighty.
Alrighty. So this is the last session, so thank you for sticking around. I'm going to do some brief exercises. Everybody get up. In your seat. Get up, get up, get up, get up. We're going to do like maybe a little bit of like shoulder rolling. Let's all stretch up a little bit. Maybe do some jumping jacks. Yeah, come on. Work it. There we go. Get the blood flowing again. We've run out of coffee. So this is what we're doing. Okay, cool. Thank you very much for PyCon for having me. I got into Python probably 6 years ago, and one of those people is in this room who actually got me very much into the Python community. Simon, where's he? Right there. Thank you, Simon. So thank you very much for having me 5 years later. So who am I? I work at RetroRabbit. I consider myself a senior software developer. Someone once called me a full-stack ML engineer, which I thought was interesting. And I'm currently building NLP stuff for an app called Kaleido. Disclaimer, first of all, my background comes from deep learning and computer science. I've been working with kind of medium-sized data sets, which is very small for deep learning. I also come from, yes, computer science. Sorry, I have zero stats background. So hopefully those lessons will generalize. If they don't, I apologize. I also tend to, all those lightning talks we just had, the entire hour is going to be like this now, because I tend to shove as much into keynotes as possible. And I have to say, throughout the conference, there have been some amazing talks, and every time I watch something, I'm like, oh, yeah, I need to put that little mention there in my talk. So I've shoved more. It was already at like 60 slides, and now it's gotten up to about 80. So it's going to be mad. Apologies. Let's go. Cool. What is machine learning? This is the last slide where I talk about this. You get some data, you build a model, train it up somehow, and you get some knowledge out. I'm sure we've had some amazing talks about machine learning at this talk during the PyData track, so I'm not going to do that. In fact, here's all the things I'm not going to do. I'm not going to teach you what machine learning is, because you can Google that, and hopefully like you've learned throughout the conference, or you already knew. I'm not going to teach you how it works either, because we've had some amazing talks on that. I'm not going to tell you where it is used, because you can just basically everything on your phone, on the internet, is currently powered by some sort of basic machine learning, maybe just stats, you know, in disguise. That's all it is, really. And I'm not going to advise you on which algorithm to use. So what am I going to talk about instead? First of all, let's quickly review the machine learning landscape. Quick question, is this cutting in and out? Because I move a lot. Is it fine? Okay, tell me if it starts cutting out, because I tend to run up and down. So we've got all these courses. You want to get into machine learning, you go do some MOOC. There's Stanford's one, there's Fast.ai, there's DeepLearning.ai, which is Andrew Ng's. You can go see this guy, among other billions like him, Siraj, he's quite cool. But there are loads of YouTube people with hours and hours of ways to learn. Isn't that cool? Google Colab, this is released about a month ago. It's kind of hosted notebooks, but you actually have access to GPUs. And you can share it, so they're kind of going for like a Google Docs vibe. And if you want to code stuff, it's really easy. I mean, you know, that's Keras, and that's an LSTM, which is a really complex neural network. Back in the day, you used to have to code those by hand in C++, and it was really unfun. But that's where we are now. That's 5 lines. In fact, to train the neural network is another line. What? It's more lines to get the data in. So obviously, we've got all these cool tools. TensorFlow, the big one everyone likes. I also like PyTorch, very cool. I'm not a big fan of Spark. I can't even remember what the one in the corner was. But basically, everybody's got their own open source AI library. Cool. So this is kind of lay of the land. This is good. Got loads of algorithms. I've got really fast-paced research. It's actually hard to keep up, but you know, doesn't matter what you want to do. There's probably a little play example out there. You want to, you know, actually go generate a Trump-like tweet generator. I can give you 4 hours and you'll have one, right? You'll have downloaded the data, found the code, trained it, and you can probably deploy it in half an hour too. Then this is cool. You've got researchers doing things all the time. Research is really beautiful to be able to do now. Back in the day, that machine learning research was a bit of a nightmare. Now it's amazing. But we've got another problem, and that's doing it in real life. And by in real life, I mean you've got a client paying you to make the model work. And they're paying you lots of money, and you better make the damn model work. and all the caveats that come with that. And what does working mean? All these questions get really, really difficult. You're laughing, but cool. So there's lots of work to be done. We've clearly solved algorithms and code, and that's all beautiful. But we haven't really figured out operations yet. Engineering, there's a lot of that wrapped around, which you don't really consider. Ethics, I'm not even going to talk about ethics in this talk because I need another 2 hours to talk about ethics. And I actually made a promise to myself last year that I wouldn't do an AI talk without bringing up ethics. So this is me bringing it up and telling you not to forget about it. My next talk will be on ethics completely. Interpretability, big one. What are these black boxes doing? Causality, neural networks, for instance, only tell you that there's a correlation. They don't tell you like if X caused Y. And that becomes very dangerous for interpretation if people don't understand that. And uncertainty, so how can we model uncertainty within our neural networks or any other machine learning technique? Cool, so this is my OSD, the overly simplified diagram. We use it to kind of encapsulate the whole process. It's overly simplified, as one would do, because otherwise each of these we can unpack and look into them in detail, which we're going to do. So you have some data, cool. You have some algorithm, you can train it, cool. You have a model, great. Probably analyze it a bit, see is this one a good one, is it okay, okay, cool, and then we have to get it into production. Awesome, and you've got some lines connecting them, which we'll have to outline in detail. So the first thing I want to talk about, there's a very wonderful man called Nando de Freitas. He's one of the top guys at DeepMind, he's amazing. You can go watch his videos on YouTube and download his books and things, he's wondrous. Anyway, at the Deep Learning Indaba a couple of weeks ago, he said this, he said, it all boils down to simple, humble iteration. And that brings to mind when we're thinking, what we think about software, we can also bring in with machine learning. So software we have agile, we probably need to look at the same kind of things when we're deploying and building machine learning models, in most cases. So let's start with the hard part. Anyone who's tried to do this in real life knows that data is the hard part. Oh, these are my little drawings. I scribbled them down, so afterwards I'm going to ask you to rate my drawings. There'll be a link, you can come rate my drawings. That is a data pattern, would you ever have known? So yeah, your data is gold. People give away their algorithms for free because they know that data is where actually all your value is now, and what you do with that data and how you look after it. Data is also pain. You'll spend 80% of your time working on your data and 20% actually training and doing the rest of it. I see this a lot, particularly when people come from stats backgrounds. They tend to want to put their data on a CSV and just kind of pass the CSV around. It's probably on a hard drive. Maybe it ends up like in a Google Drive folder. Can we not? If we can, if possible. So if it's not big data, we can try version it, particularly if we're working with data that is very valuable. Let's try version it. If not, put it in a database. So it's with backups, so we can store it and we can look after it. Let's have a nice tested data pipeline for getting things in and out so we don't damage it. The deep learning field, everyone's like, oh, I've got this folder of images and I've got this CSV and I'll add some more when things go wrong. And later on, you suddenly forget what you added and how that impacted the model. So data version control becomes something you don't think about initially, and only later on do you realize you very much need it. If you're the type of machine learning model that you actually need to create a lot more features, so you're very involved in like your feature engineering, and you kind of want like a more processed-oriented data version control. Oh, I seem to be missing something. My animation screwed up. At the bottom, there was meant to be one that said one focused on more adding data, so more data-oriented. And that way you'd have kind of data-oriented data version control. The slides that are missing, I actually talk about 3. So one of them is Quilt, that's very data-oriented. So that's very much kind of like you add a chunk of data and then you commit that and you can push it. On the process-oriented side, where they say it's kind of like database migrations, you kind of you store code to show how you got from one step to the next step. They've got one called DVC, dataversioncontrol.com, you can go get it. I tend to prefer using Git. Git large file storage, it's a bit messy, but it kind of gives you the best of both worlds because I can kind of store my migrations with my data changes. Your data will never be perfect, and you should try and improve it over time. Once again, humble iteration. Ooh, I moved the slide. That's what happened. There we go. It's beautiful. I've found those logos. For each of your patterns, if people go, I've got some patterns, cool, great, I've got some data. Try store its birth certificate. By birth certificate, I mean source. Source, who created, who labeled that pattern? Where was it found? Where did you get that data? Because some sources are more important than others, and maybe you want to include that in your model. Creator data becomes really important when you want to figure out what changed when, to be able to track things over time, to figure out if there's drift in your data. So always make sure you store these, and then I also store a status to figure out, okay, well, is it part of the training set? Is it something that's been labeled or needs to be labeled or we've determined is redundant? And this is the sad truth of the world. We live in a world of bad data, and it's real, and we'll probably never get away from that. It's inconsistent, it's largely incorrect, it's definitely not representative of what's actually happening, and sometimes that's all you've got. You got nothing else to go on except your bad data. But this is okay, because in the age of these really powerful algorithms, sometimes your algorithms are powerful enough to be able to handle that bad data. And bad data can get you sometimes 80% of the way. So you work with your bad data. This is all you have in your first iteration. You've got some data, cool. Build your model. You'll get some sort of accuracy. Work on your test set to bring that up to speed and make it as good as possible. And then the rest of it, you'll what do we know? Improve over time and humble iteration. Once again, iterate your data. Your data will get better. Work on your data. Take time to make it better. This is a weird thing I thought of. I thought of because I thought of it 2 months ago, and I was like, why didn't I think of this 3 years ago? Because at the time it didn't seem important. Do we need continuous integration for data sets? What does that mean? Well, I've got some major, if I think in Git, I've got my important data, and I've got some changes that I've made to the data. Maybe I added one, maybe I updated some labels on some patterns, maybe I removed some. And sometimes you make mistakes. And mistakes can actually have quite a bad effect. So I was like, yeah, I want to see how my data, when I push it to Git, I want Git to run some tests on it. I want tests for my data. Why am I not testing my data? I want to validate the types of the things I've added. Sometimes I leave out fields, and they could have been easily fixed. I want to validate that my distributions have kind of stayed the same, to validate that my number of categories are kind of balanced. I want to check for duplicates, if those, that matters to you. Check that things aren't missing. Stupid things like that become really, really, really important later on. So that's data. Cool. This also means, how much time do I have? Because I think I'm about halfway now.
Yeah, so you have probably up until, I have to check the schedule. Yeah, 5.
Up until 5, what's the time now? 20 past 4, we're doing well. Training. Training is the easy part. Why? Because we've got lots of nice things code that you can download. If you want to do some computer vision, there's probably some TensorFlow code you can download to train it. But still, it's code, right? So version it. Put some continuous integration on it. Unit test it as far as possible. It's really hard to unit test kind of machine learning code because there's always some stochasticness in the models and in the training. But there's some great articles. I think there's one awesome one that I think I'll tweet. I didn't put it on this presentation that Google wrote about testing your machine learning models. Cool, we got this added in earlier. Someone was asking about how do you choose your architecture? So you've got a neural network. How many layers do you need? How many neurons, hidden neurons do you need? What are your learning rates? What do you how do you choose those initially? And someone said, well, you kind of pick them and you handcraft it. That's one way. One cool strategy that Andrew Eng mentioned was try overfit your data set completely. So have a data set, remove all kind of, usually have your test, your development, your training data, and you usually only train on your training data, and then you kind of use your dev set to kind of regulate when to stop training or to check if you're overfitting. Overfitting is when you learn your data set exactly and it can't generalize to other environments. But he says, in order to figure out what sort of architecture you should be using, try overfit your training set completely. Don't regularize it, don't do early stopping. Overfit it completely so that you know that your neural network has the capacity to learn everything in that data set. And from there, you start addressing overfitting. So from there, you add your regularization techniques such as dropout or L2 or some of these other techniques that exist in order to enable your machine learning model to generalize. I thought it was a really useful strategy because I'd never thought of doing that. I kept trying to keep my model small. I said, oh, small is better. And actually, I was limiting the performance on my model by keeping it too small. And I eventually learned, okay, make it big enough that it can overfit. And once I've done that, I will deal with the regularization afterwards. In terms of what you should choose your learning rates as, what you should choose layers and things like that, there's a whole field of hyperparameter search. And And I'm not talking parameters in terms of like the model's parameters, I'm talking about the training algorithms parameters. And there's a couple of cool repositories. This one's called Talus. It's one that you can use with Keras, which is one of the top models. I think it works with TensorFlow too. And that enables you to kind of help you search for what the good parameters are. Very cool. Cool. Something you never think of. Really obvious, but you never think of. Usually you have some code, it spits out the model, then you change the code and it spits out another model. And later on you're like, what did I change to make it better? There was no tie between the model that got spat out and the code that generated it. And that becomes really hard, because if I want to improve it, how do I need to know what made it worse and what made it better, you know? And often what makes it worse is the worst bit. When you change something and it makes, you know, your performance worse, you really need to be able to get it back to whatever the state was when it worked. And if you haven't got like some sort of, you know, rows in a database or some sort of Git tags or something to help you along with that, you're going to have a really hard time. Similar vein, it's really helpful if you can kind of know what data generated this model. That's a little bit harder to do depending on the size of your data, but also really useful to keep in mind. Yeah, so that's pretty much training. Training is actually easy. Let's talk about the models. This is my neural network. It's a model. It's a SIR as well. Your model should be treated like a config. So it comes out in probably a whole bunch of matrices, basically. Treated like a config. If you can store it in a technology-independent way, you can do that. Thankfully, everybody's kind of supporting the same format. So Keras, which supports TensorFlow and supports, I think, PyTorch underneath, and supports Theano and a couple of other ones, they tend to determine the standard of what gets moved around, which is cool that it exists, and you can do that. Once again, also, if you're not going to version it, I actually don't like versioning it. I like storing all my models somewhere. So I store it on the cloud so it never disappears. I make sure that the name of that model is tied up in a database or in Git somewhere that I can relate these things. And later on, if I want to pull down or rerun my updated test set on all the existing models I've trained on, I can actually go do that because they're stored somewhere and they haven't been lost in like the hell of some file system. Cool, another big question. When is your model good enough? Because you're rarely going to get 100% performance, and if you do, you're probably overfitting. Or you've got really, really, really good data, which is really rare. You must have a very well-spec'd problem or quite a easy-to-do problem. So when is the model good enough? And I think one of the things you have to do, particularly if you're in consulting, is you have to kind of have this discussion with the client kind of upfront, that the model's not going to come out with 100% accuracy, and that's okay. And you need to convince them that they need to improve it over time. So when I say when is the model good enough is when it adds value to the user. Adds value, that's also quite a tenuous term. We could unpack that for a while. If you have no existing model and there's nothing there, then something that kind of gets a 60% accuracy might benefit a couple of people. That could be 60% less work that someone has to do, less manual labor that someone has to do, and they could spend doing more important things. If it's health, that's a very, very different question. So in health, I think we had a talk about that, about how that's a far more complex field when it comes to doing machine learning there. Because a half-working model, you could convince someone that they have cancer when they don't, and things can get very hairy from there, or vice versa. But a lot of the models we're working with are kind of user-facing, and then it just needs to add some sort of value. So the first models we built, I think they were only kind of 2% better than the previous system that they'd used, and the previous system was kind of a hand-crafted, hacked-together rules kind of system, and it was only 2% better. But that was a good start. 2% better, deploy that, and we'll learn something about the models and from the feedback. So deploy them sooner rather than later, if you can. If it's not somewhere drastic like airplanes, I don't know, flight paths or something, or health. If you're just doing something where nothing exists or when you just need to compete with an existing system, rather do it sooner. Don't wait for it to be perfect. Humble iteration. I drive home. Humble iteration. Iterate everything. So that's our model. Analysis is fun. I don't come from any sort of statistics or any of that sort of background or any, and these days I suppose you can get data science degrees. Back in the day those things didn't exist, so analysis was kind of an interesting field that I've been kind of picking up as I go. So you get your kind of basic data analysis, your exploratory data analysis. You get something called error analysis, which is kind of looking where your machine learning went wrong. Get certainty analysis, how uncertain is your model, interpretability, so that's just looking at actual instances and seeing if you can interpret what the neural network's doing. And then kind of basic performance, so how well is your neural network doing. Let's talk about performance metrics. So whatever you agree, so usually you agree on some sort of metric. It's accuracy, or it's some sort of error metric, or it's some like F1 score. You'll have that, I think we use an area under the curve, because we've got a classification problem. And we set that up front. We decide between us and business, like this is what we're going to use as our metric. Businesses kind of vaguely understand what the implications are and what their influence over that number is, and then try to get some sort of sign-off and agreement on that, because it's important that they understand what they're going to be deploying, so when it doesn't work or it works in a different way, they understand that behavior. This is a lesson I learned from Andrew Ng. Have one number that tells you how good your model is. Often you get a couple of numbers, F1 score consists of two other numbers, and having those two, you kind of got to decide which one to balance. So now how do you know when one is better or one is worse? And there are a couple of ways to get that one number down. A cool example is this one. You start off with one number. You start off with a basic estimate. Okay, we're going to use accuracy, or we're going to use area under the curve. And then, for instance, if a user reports, oh, what happened? There we go. Has that been happening the whole time? Really? How often? Okay, just shout if it does it more, because I'm not looking there. Why is it we can't get projectors right as a species? I got it. Like printers. Oh, printers. Scanners seem to be doing the same thing. Yeah, anyway. Wrong model. Do they get better than this? I don't think they do. I think they all suffer from this. This seems to be a pretty good one. Yeah, so if your user reports that your cat classifier starts classifying porn as cats, then you should probably add a really big penalty to that number, so that you update your equation for calculating how good a model is to say, okay, well now we're going to have accuracy minus a giant chunk when it classifies one of these test patterns as a cat. So then the idea is that you can kind of grow this metric over time as well, which points back to humble iteration. So you have a performance metric. Your performance metric should update over time, because you're going to discover things about your users, and you're going to have to try and integrate that feedback back into the model and your choice of the models. Cool. Error analysis. Just basically looking at things that went wrong. So you get some sort of accuracy at the end. You want to go look at what happened and what went wrong, so you can try and understand the underlying cause. So you do something really boring. You take a spreadsheet and you put them all in. And you go through and you look, okay, well, these are the ones that are most misclassified. Let me start, talking about them. Let me start looking at them. So then there's one that's talking about lessons and coach, which you've picked up there's a problem. There's one which is referring to languages. There's one which is referring to social media. And you start building up these kind of categories for what your problems could be. So this is some actual data that I stripped from one of our projects. I've got a classification error that's basically completely misclassifying. Occasionally I say hard problem, because that's something I know a neural network would have a hard time deciding, because I personally would also have a hard time deciding whether these two are kind of semantic matches. But don't worry about the detail of the content here. Worry about that little reason at the end. So what you end up is with a list of like, cool, well, this is where my model's failing, is on these patterns. That dev set you should also improve over time, so kind of gather data of outliers. So when you pick up that it's behaving badly, either through user reports, something like that, add those to your dev set or your test set. Regularly try samples production data to keep your stuff up to date, to see how it's performing there. Always use those kind of well-known contrived examples that you think would break it, because that becomes quite important, and from there you can learn quite a lot. And you also improve that dev set or test set over time. The next question is, cool, you've done this error analysis and you've determined you've got this bunch of problems, probably with your data. Which one do you work on first? So I try to calculate the impact of those problems. So the number of users affected by the fact that our neural network misclassifies things to do with social media. What is the impact? How many users are adding content related to that? And I take that impact and I look at the error that it's having on those patterns, the average error, and I multiply them together, and now I have a metric that says, cool, this is the impact, the number of users, and how badly it's performing. So if it's something that affects 1 or 2 users, even though it's misclassifying really badly, you won't prioritize those, right? You'd prioritize the ones that are performing really badly and affecting a lot of users, or even the ones that are performing okay-ish but are affecting majority of the users. And this way you can kind of build up this priority and pick which problem to work out. So now you know it's working really badly on social media related, data patterns, and now you can go, cool, let's go look at that data and see what's wrong. Let's gather more data around those types of things. Let's go search production and see if we can get some label data. You can also do this, which is really nice for clients. So each of these lines, a little pink one, come on, projector. It's because I'm moving too much. Each of these lines are basically a problem I identified. So think of one of them, the pink one classifying porn as cats, and one of them could be doing something funny with social media, whatever the deal is. And these are all different. At the bottom, I've got my candidate models over time. So these are the models I've chosen to be the best out of the things I've trained that we're kind of watching. And up here, I've got the classification errors. In fact, you can use classification error times that impact, which I referred to earlier, that metric. And this is great for a client, because I can show it to, and they'll be like, how's it doing on that cat porn problem? And I can be like, well, here's a graph that shows you that we're getting better at it. Or and they've got, what about the social media one? Oh, we're getting worse on that, but we're solving a whole bunch of other ones. And that's really useful. Clients love this. You can also do this. I gave them an interface where they could identify their own problems with the model. So they come, it's not working on this. I'm like, great. Here's an interface. Add a problem. So here it's got like kind of a name, some description. And then I said, cool. Well, here's another little interface. Over here, you've got basically the same thing, but some extra test patterns. So they can kind of say, I say, cool, you've identified a pattern. Tell me how that should work. Give me 10, I think I capped them out of 10. I said, give me 10 patterns that you can generate on how this problem should behave and isn't. And that way I can also then run the metrics and say, okay, well, it's not performing as badly as you thought it was. This was obviously a fluke on that one pattern. Or I can... I can at least now track it over time. So then I can build up this kind of picture over and over again. Cool, so that's error analysis. How are we doing for time?
Yeah, well, actually, we probably might want to end a tad earlier in order to have time for Q&A. But yeah, let's say 10 minutes at most.
10 minutes? I think I can fly through this in 10 minutes.
A few more minutes if you want.
Yeah.
Started late.
Cool. So neural networks are black boxes. Anyone who's used one knows this. It's really irritating. We had a talk about random forests. Random forests are great. Clients love random forests because they can actually get some person from, I don't know, there are a lot of AXIs here, but usually it gets sent to, I'm from the dev side, and it gets sent to an actuary somewhere, and the AXI is very happy to go through and validate the decision trees. But when machine learning and the neural network side of things, interpretability becomes an issue. So this is a picture of a wolf. I think we can all agree. There's this great story about how there was a group of people trying to train a neural network to distinguish between dogs and wolves. And they were getting amazing accuracy and was doing really well. And they went to the zoo and they took a picture of a wolf. And it classified as a dog. And they couldn't understand. And they ran it through what they call an explainer. And they realized it was picking up the snow. And it was never actually picking up the wolf. So as soon as it saw snow, it was like, oh, that's a wolf. And as soon as it saw anything else, they were like, oh, the background, it must be a dog. So when you actually run an explainer, it looks a bit like this. So this is deciding between, it's got probably two outputs, decide whether this is a cat or a picture of a cat or a dog. And here you can see what is contributing to the neural network deciding that it's a cat. So the green bits are what it decides is contributing to, it was looking at in its decision to make it a cat. Over here they got a dog, and obviously that made it probably, no, that's probably not a picture of a cat because there's a dog there. And this is a tool called Lime. It's really, really cool. And they've got another word for this, an ablation study, I think it's called. And the idea is that you kind of remove chunks of your image. So imagine just putting like a little gray window everywhere all over the image. So you take your image, blot out a gray bit, send it through the neural network, and see how its prediction changes. And that way you can kind of determine what is important to the neural network in making its decision. And this is really, really, really useful when you're analyzing patterns and you don't know what the neural network did with it or why it decided what it was going to decide. Next thing is certainty analysis. This is something I don't know much about, and actually, and this is why I'm doing loads and loads of stuff in Bayesian related fields to try and understand that. There's actually a guy called Stuart Reed. You can go follow him on Twitter. He works for a company called Miracle in Cape Town. Very cool. And he does a lot of work with certainty because he's working with these giant hedge fund kind of models. Uncertainty is how likely the neural network or our model would have made the same or similar prediction if the patterns were just a little bit different. And you'll find out if the neural network is dealing with something it doesn't know about well, that if you vary that pattern just a little bit, it'll completely change its outcome. So there are ways to do this. You can add layers of noise into your neural network. You can use something called dropout, which is usually used at training time. You can use it in inference, and you kind of deadens parts of the network, and you can see then how deadening parts of it will influence the outcome, and you can add some probabilistic layers. I put that in, I still don't know how. One day when I've gone through all the context of Bayesian techniques, I'll be able to explain that one. Well, automate your tests. I think so there's automate your analysis as far as possible. Graph statistics, canary tests, which are basically these things that, die first, so you know that something's completely wrong. And always store your results for test patterns in a database, so that later on you can compare one model to another model or any other models, be able to see the differences without actually having to rerun them. This thing. So if you're coming from stats, you love Jupyter. Actually, if as a dev you love Jupyter. I love Jupyter still to this day. But there's this bad habit of everybody putting everything in a notebook. So sure, you had a couple of talks that were talking about making it reproducible. That's great, but I can't productionize a Jupyter notebook. I can't really test a Jupyter notebook. I see that the same patterns happen with coders. They don't. The dry principles fall away and the solid principles fall away, and suddenly there's duplication among notebooks, or you've got this one giant notebook with everything in it. People aren't writing up things properly, they're not doing the reports, they're using it as a way to code. And worst of all for me is I can't review changes. So if I've got a junior and we're working on something together, and I can go review what's in his notebook, but I can't check exactly what he changed. And then there's this habit to kind of sit in the notebook more and more and more, and they don't ever learn to properly write tests or code that can be tested. And then when it comes to taking those like this notebook hell and trying to putting it into production, it's a small nightmare. So great fun tool for analysis, amazing for demos, amazing for showing to crowds that need to approve of whatever you're doing. Just beware, don't take it too far. I've noticed this happen continuously. Okay, production. Production, the thing we forget about all the time. If you're working in like a model world, you forget about your non-functional requirements. Your throughput, your scalability, your model size. Model size, I keep seeing people wanting to put 200 megabyte models on mobile phones. That's not going to work. I see some people have apps that are 200 megabytes and you have to download them, which isn't going to work. So you see I've got my little model in a little Docker whale. I thought that was kind of cute. This is a cool story about a production problem. So I don't know if anyone knows WaveNet. WaveNet is what currently runs in your Google phone, your Google Assistant. So if you ask, okay, Google, tell me about XYZ, and Google tells you back, the text-to-voice is run by technology or an algorithm called WaveNet. And WaveNet got developed by Google Brain a couple of years ago. And they came up with this thing, they're like, wow, performance is amazing. You can hear that people, the AI taking moments to breathe. It's unbelievable. And they sent it over. Usually they just go, cool, engineering team, take over. And they sent off the model. And engineering team tried and tried and tried and tried, and they've got some of the best devs on that team in the world. And the engineering team came back and said, it's too slow. If you're going to be asking questions and getting responses, it just cannot be this slow. And there's nothing we know how to do without changing the model to make it better. And they had to put a special team together just to optimize the WaveNet model to make it actually run faster. And I think I was talking to Simon earlier, and he was saying that what they actually to do is make the model worse. So what they often do is they truncate the floats to make them smaller. So they're not 64-bit, they're 32-bit. That makes the model smaller. That's an example. Or they make the neural network actually work a little bit worse, but it actually works faster. Drop a few layers, things like that. So that's something that commonly gets forgotten. Haven't even talked about data pipelines properly. Haven't talked about infrastructure. These are all hard problems. Thankfully, these are getting solved. We have these wonderful tools, Google, Azure, ML, Amazon AI, Watson, if you still remember it. The NLP is still better than everyone else. Like, no jokes. It's still not great, but it's better. And they help you with that infrastructure problem. So now you've got these tools. I haven't used them all, so if anyone's used SageMaker, I'd be really interested to get some feedback. It's Amazon's, whole end-to-end vibe. I like Azure ML. It's got like a lot of promise. Same as the Cloud ML from Google. So that kind of solves some of your infrastructure problems. It solves your scalability to a large extent with Docker and Kubernetes and the gang. You don't even have to worry about it on half these platforms, which is great. So yeah, that's my overly simplified diagram. Still got some work to be done. We haven't really addressed ethics, and we definitely haven't addressed causality. And if we really want to be using these things in production kind of environments, that's important. Causality, I didn't even mention the fact that you can trick these neural networks really easily, so security becomes an entire issue. If I can turn a stop sign, and there's a car driving, I can turn that stop sign into a toaster, which is a really interesting paper you should look up. Important resources. Andrew Ng's Machine Learning Yearning just came out a couple of months ago. He finished writing it. He was releasing chapters as he went. It's very brief. Read the whole thing. It's amazing. So if you're doing this in production at all, you're trying to build models that you need to deploy, go read that book, particularly if it's kind of your deep learning models. Julia Evans' blog post. Oh, come on, projector. Machine learning isn't Kaggle competitions, which is a nice one for the data scientists in the room. And deep learning in Java, there were two talks about machine learning in production. One by Stuart Reed at Numerical, and another one by Emoji from GitHub, who just built GitHub's recommendation engine, which is very cool. It's not up. That link just takes you to the talks, so just keep checking it. They'll eventually appear. Very, very, very good. Cool. Question time. I like questions. Also, if you'd be so kind, please read my talk. It's anonymous. It's a bit.ly/PyCon talk, and then I've got a little survey. I like to hear. I am sensitive. I'll cry by myself. It's fine. But you can be mean. It's the only way I'll go. And if not now, we can talk by the beer. Thank you for having me. Let's do questions. Yes.
Alrighty. First question.
Can you talk about ethics for a minute?
Let's talk about ethics for a minute.
If you feel like it.
No, it's fine. I saw someone asking a question, but did everyone get scared?
Well, I mean, we expect. Okay, so you don't want to answer that one.
Or ethics? No, I don't want to answer briefly.
Oh,
so
I see. Okay.
Ethics goes into a whole thing about.
Do
you want to ask me about ethics? Because ethics goes into a whole issue. I mean, I saw there's a great talk from NIPS last year. Go look it up.
All right, I think that suffices then. Okay.
Yeah.
Any other questions? Also, I forgot to mention, we have 2 last vouchers from Microsoft for $100 in the cloud worth of the Azure cloud. So good questions, get those.
Ooh, I have a question. I'm wearing a Microsoft shirt. Will they give me Azure credit so I can give it to some researchers who really, really, really need it?
They'll probably, maybe they will, I don't know.
I've been harassing them. I will give it to the researcher. I don't even need it. We get company ones. But
this is a strange ethical dilemma.
Yeah, no, don't give it to me. I'll go harass them directly. We can just talk afterwards and I'll get more from them.
Okay, I'll wait for your talk next year about ethics. All right, any other questions? Okay, one question over there. Actually, I'll take my mic.
I know you guys want to go home, so thank you for sticking around. Is there beer afterwards? Sorry, I keep asking questions. Yes, good, okay. Yeah.
Thank you. So you mentioned that notebooks can turn into an absolute nightmare. So I was wondering whether you use them. If you don't, what do you use instead? And if you think a co-laboratory might be useful at least in the collaborative aspect of working together on notebooks, or if there's some other kind of versioning thing that you could use, I don't know. What do you prefer?
So I'd say we always start in notebooks. So you start there, you play. I like Colab as a collaborative tool to be able to do things that way. It doesn't help as much with versioning. They're actually still figuring that out. But I still say play, learn, understand, do all your exploratory data analysis in there as far as possible. But as soon as you realize there's a process and something needs to be repeated, and this needs to become part of the final thing, you put it into like a .py file, and then you write a test. So it's just this kind of discipline that you have to bring back in. And it's weird because we talk a lot about TDD in the software engineering world, and it's just kind of still done a little bit backwards because it has to be, right? We have to be able to explore. And as soon as we know what we're going for, then let's go back and let's write our tests and, do it properly. So I'd say let's start there and just be disciplined enough to do that early enough, and not like 3 months down the line you have to pass it off to an engineer who has to take this stuff and make it some production code.
I also just want a quick reminder, if you think a question is a good question, just say a good question as well.
I thought that was a good one. Yeah.
Oh, okay, well then you go on. Right, next question.
Hi, so there's this platform in South Africa that is like Kaggle called Zindi that just launched.
Sorry, yeah.
And it's really cool. And we're probably about to launch a challenge to help
Is it
farmers
you
using
who's
it.
doing Zindi?
We might be
awesome.
soon, but we know them.
Okay.
They're friends and they're really
Yes.
nice people. But
Cool.
machine learning is not Kaggle. You just told us that.
Yeah.
So maybe like a pathway for taking these insights that come out of a Kaggle-like competition or a Zindi competition and how those could make their way into production. What would be the next steps or the things to help people?
So
get
I think,
into production?
yeah, the trick is to elaborate on why Zindi is not, why Kaggle is not machine learning. And I think the main thing there is many of the Kaggle data sets you get, and they exist. And someone's already been through them. And, often we get to projects and there's no data. And I'd say that's the biggest difference, actually, is first of all, the data is largely there, and it's largely in some processed form. There are a lot of ones where they aren't structured, and those, I think, are the more realistic ones. So that's the first thing. And I'd say still practice the Kaggle to get, because Kaggle's amazing. It's an amazing tool to figure out how to understand the insights, as you say. And then take that and then try, you can still try, take what you learned from Kaggle and try put that into production. I would just try put it into production. But then the trick is to have that going forward. So it's good to practice the tools. It's good to get something there. So you could take what's learned there. Then we've got to think forward. It's like there's more data coming in. The data is going to change over time. How can we update the data set? And then you're going to have to start, that's where the kind of data wrangling part comes in of how do we keep our data up to date? How do we look after it? And how do we gather feedback from the users from production environment and add that back into the data set? So I would never say that Zindi or Kaggle aren't a good place to start. In fact, they're way better than trying to do a Trump tweet generator for fun because you're actually looking at proper insights. So yeah, I'd say always start there. It's good from there. Try deploy something. I don't know what the paths are going forward. I suppose you just give the model back to, or the code back. I don't know how the Zindi process works afterwards. What happens after that, but it would be cool to have the person who maybe won the competition be involved. Yeah. 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 Oh yeah. What? That's great. What do you do? I would say put it in production. Always, because you have to have a model. You have to get some sort of feedback on it. Step one, put it in production and try gather feedback. Start using it. So I put an API in front of it and see what happens. And from there you start saying, okay, now we can see where it's going wrong. So then you start gathering insights. You start playing with it. You start doing extra analysis. And yeah, so as a platform, getting these models back, I think putting it up there, like I said, rather get it up there sooner than later. I'm very big on put it up as soon as possible, particularly if it's going to benefit someone immediately, even if it's not in a 100% way, if it's in a sort of way. So put it up and then go back and try put your data processes in, particularly if it's something that's continuously the data set's going to grow. If it's not that kind of problem, then it's a matter of looking at just continuously improving the models further. Yeah, I don't know if that answers the question. It's a good point. It's also a good question. Sorry, I'm giving out these.
Okay. Righty. Okay, and the next question. You have one?
One more question.
Yes.
Yeah. Where?
Sorry. Order. She was here first. Sorry.
Oops.
Sorry. So have you considered using machine learning models to help you with error analysis, like maybe putting shit into self-organizing maps so you can categorize?
Yeah, so unsupervised learning is a really cool tool to be able to do that. So I have done it a lot.
Oh, how is it?
Yeah, so I haven't done it with a SOM, but are you doing SOMs? Because I've got friends doing SOMs, and they feel a little alone in the world because they don't have friends who are doing self-organizing maps.
No,
but
I
anyway,
didn't do those, but they're really cool.
yeah, they are cool. So I've been actually considering putting one in, but I've been largely using things like TSNE and PCA, that kind of thing. And then you kind of just plot them out, and you can see, okay, label them all. Be like, okay, there seems to be a problem here. Everything's red. Okay, what's similar there? Okay, I understand.
Is there still a large manual component in error analysis, even with the help of those?
Yeah, SOMs, I think they've got some auto-labeling. I don't know how well it works.
Yeah.
There's still a large manual component as part of that. So, but you could. The problem is then you're playing a game of this model training against that model. I don't know, it seems a bit hairy. the reason the models aren't doing well is because it couldn't figure it out itself. So there's clearly something very wrong. So I would say yes, there's still manual process. If you could solve it with auto-labeled SOMs, that would be a really cool research topic, and I think you should do that. Yeah. I know people
but it sounds hard.
Yeah.
Right, next question.
Yeah. So what's your thoughts around data science team size? Coming from a software engineering kind of background, in fact, not actually a real Python developer I am, but yeah, what are your thoughts on the data science teams size versus like, seems like very, very small people work together on these topics, whereas in software engineering, it's like people want to get more developers and more teams. Like
this is also a misunderstanding about how software works. So adding more developers to the project doesn't always make it go faster. In the same sense, adding more data scientists to the project won't make it go faster either. But in terms of, you're talking about more team size, team composition, because that's an area I find research really, really interesting, because I've tried putting together teams, because I had to do everything from end to end. I was the one person who did the data all the way to actually getting it in production by myself. And I got quite familiar with the roles, but then I also got quite familiar with like the kind of entanglement between some of the roles and how close you'd have to work together. So I think you should always have a buddy, data scientist, data engineer, buddy together. I know at the kind of Googles and Facebooks, they team up as, at least in the research hubs, they're research scientists and research engineer as buddies, and they work really closely, and they kind of bounce ideas off each other. So one's got like more of an engineering background and knows the practicalities of doing it, and one's got more like the statistics background and knows what should and shouldn't be built. And I think if you kind of grow it in those pairs, that would be really interesting. And I haven't seen anyone do that. In terms of, like I said, in terms of adding more, people want to grow developer teams because there's just so much easy development work that just needs to be done. Whereas data science, they don't even want to spend that much money on it sometimes. So they're like, oh, keep it small, they're expensive. We don't know what to do with them yet. And that happens. So you get the guys who can hire the one data scientist who kind of sits there and has to basically write reports for people, shame. And on the other side, you've got 20 developers sitting at some unnamed telecommunications company, which I won't go into, and you've got 40 data scientists sitting doing nothing, is the other side of the coin. So data science team, I'd say, relatively small, relatively lean. I always say with software, you shouldn't have more than 5 people working on a particular end. So if you're a back-end team, there shouldn't be more than 5. If you're the front-end team, there shouldn't be more than 5. You can microservice it out, and then you can probably have a couple more groups of 5 working together. And I'd say the same in a data science team, probably with a nice diverse set of stuff. Don't go more than 5 in a particular team on a particular product. And probably not just data scientists, mix between people with more data expertise and people with more like engineering expertise. Yeah, hope that answers.
Okay, we have one question here. We actually have 3 minutes left for questions.
Okay, I hope I'm not taking anyone else's question time, but you briefly had a slide about all the cloud solutions that you're using. I wanted to know what your experience and your personal preference is, and also just like exploring a little bit more into the your pipeline, your stack, and like how you productionize, just like a little bit of the technology you use there, just out of curiosity.
So this leads me on to I don't know if I can mention
it. Sorry, actually, I'll keep it a little brief because that's the second question, and there's 2 more after this. This is the second question, and there's 2 more after this, so just a little briefly.
Oh, brief. Keep it brief. Come to DevConf, we're doing a talk called Cloud Shootout. We put them all against each other, is the quick answer. Do I have a preference? Much of a muchness. Azure ML got there first in a kind of most solid form, if you're going to go that way.
Okay, next one.
Hi. You mentioned just in terms of like working with clients, so when you're implementing a model and they're not necessarily happy with it, or it's not what they paid you to do, they expected more. How do you manage those expectations? More specifically, do you have a framework for managing client expectations?
Oh, that's such a good question. We need more things because that's such a good question. Do we have a framework? No, but I heard there's a guy called Peter, he works at a place called Mint Technologies, I think, and he works in that kind of field. We also work in machine learning. And he says his day one, he walks in and says, you're going to pay us a lot of money to do something that probably won't work. It's upfront. Says that, cool, are you ready? If it works, it'll give you a lot of value, but there's a high probability it won't work. And he actually phrases it like that. And he says, people go, sure, yeah, that seems honest. We're willing to take this risk. And from there, we try show them, you've got to get them into that whole change management of like, if they're not really on the agile bandwagon, you've got a long way to go. If they're really kind of on the Agile bandwagon, I don't like calling it a bandwagon, because it's, anyway, could have be a conversation about that. Then it's easier, because then you can kind of show, oh, we deploy every 2 weeks. We can choose to we're ready to deploy a model every 2 weeks. We can get better every 2 weeks. And you say, well, it's bad now, and you're trying to convince them about what you'll learn. If you get it out now, what you'll learn, and you can even go back and be like, hey, investor people, look at what we have done. Or not investors, but mid-level management, you've got their checklist. We have AI in our thing. Excellent, checkbox for the year. No offense to anyone in mid-level management, but they don't, you get these giant corporates, they don't actually understand, and it's a really hard process educating them about it. So do we have a process? No, we are struggling along. I enjoyed your talk earlier because I was like resonating. But yeah, it is quite difficult. So if they've already got software teams doing Agile, then it helps a little bit. But also like go in and be honest and be like, we're not going to promise you the world. We're going to promise you it's probably not going to work, and we're going to strive for this % accuracy, but make that strive aiming for 80%, 85% kind of thing. Never make it 100. Never convince them it's going to never even say that it's going to work perfectly. And if they're not happy with that, then I don't know. Then you probably shouldn't, they probably need to come to your side a bit more. Then I don't know what to do. You have to show them more. Like I always try to take them along for the journey. Look at what we did. Show them little iterations and get them a little bit excited. But yeah, another topic for another day. When I figure it out, I'll tell you. What?
Why not add versioning and testing to notebooks?
Is that a thing we can do? Should we develop it?
We have a Turing-complete programming language. Surely it's possible.
Yeah, we do. So we could do it. We could. I think we should. I will contribute to that repo. Because why aren't we doing it? Why aren't people doing it? I think people see it as an exploratory tool. We should probably be testing our notebooks somehow, in a way that doesn't let the notebook get away from itself. So let's build that thing. Who's in?
Okay,
yeah.
Great idea. Okay, that's enough for questions. It's 5, so I'd like you to all give a round of applause and thank her.